Welcome to a lecture on Introduction to Matrix and Sparse Matrix. In this lecture, we are going to study about what is matrix, complexities of operations of a matrix, advantages, disadvantages of matrix, what is sparse matrix, and the representation of sparse matrix. Matrix, it is a collection of items of same type arranged into fixed number of rows and columns. Here we can see one example where 4 rows and 4 columns we have taken, and for every row and every column some value we are representing. This value, it is integer value we are considering. So we can say that this is the matrix we have created to store integer data in 4 by 4 dimension matrix. In day-to-day activities also we make use of matrix to store information. Consider I want to store marks of 10 of every student with his roll number. Here we can consider that each row will represent every student and column will represent number of courses for which I want to store information. Similarly, some other applications like if I want to perform object transformation in computer graphics, I want to do scaling, rotation, or translation of any particular object in computer graphics, we are efficiently making use of matrix to perform this operation. Similarly, to solve linear equation, to get the solution for linear equation by making use of different algorithms like Gauss elimination method, Gauss-Seidel method, Jacobi's method, we can efficiently use matrix to perform these operations by these algorithms and get the solution. Nowadays, in machine learning also, we are making use of matrix for recommendation purpose. Like if number of users are there, they are giving rating for different movies, songs, or products, and we want to recommend movie to other user. So here we can say rows will represent different users and columns will represent different movies or different songs or different products. And for every ith row and jth column, some rating will be stored, which is given by ith user for jth movie or song or product. So this way, in day-to-day life, to solve our problem, we can efficiently make use of matrix. On matrix, we are storing data in number of rows and number of columns. So to read information from matrix or to store information in matrix, we require the time that will be order of n square. So we can say time complexity for reading all elements from the matrix or to store elements in matrix, it is order of n square, where n represent number of rows and number of columns which are considered for that particular matrix. We can perform addition, subtraction, or transpose of any matrix. So for that also, obviously we need to read each and every element from the matrix and then we can perform addition or subtraction of that. So similarly for the matrix addition, subtraction or transpose also, we require complexity that is a order of n square. Here we can see this is the code which we can find from which we can come to know how the complexity that is order of n square is coming. So here I can say m number of rows are present in my matrix, n number of columns are there in my matrix. If I want to read or print complete matrix, then I can say starting from 0th row, I will iterate this inner loop for all the n number of columns which are present and I will print the information at A of ith row and jth column. So here we can see the inner loop is going to execute n number of time for every I value which starts from 0 to m. And because of that, we can say the complexity, it is coming as order of n square. Here m into n, we are considering m will be the number of rows, n will be the number of column. If m is equals to n, then it is going to come as a 2m square, 2m square plus 2mn plus 1. So that's why its complexity, it will come as a n square. Same thing will be applicable while storing information in the matrix as well. Addition of matrix when we want to perform, suppose we have two matrix passed having number of rows m, number of columns n, then we can say for every ith row and j column is going to iterate and read every column value from both the matrices, and it is going to perform addition of that, and it is going to store at the ith row and jth column. And because of that, addition of all the elements into matrices, its complexity also will come as a order of n square. If I want to take transpose of a matrix, transpose, it is nothing but you are swapping ith rows to column and columns to rows. So here initially in the matrix m rows were there and n columns were there. After taking transpose in my resultant matrix, I will be having m number of columns and n number of rows. So I have to swap each and every element, and from the matrix, from ith row, it will be coming in the ith column, and from jth row, jth column, it is going to come at the ith row. So that's why I have to read every element and I have to swap that to the other location. Its complexity also will come as a order of n square. So now here, if we consider even in the multiplication also, we need to multiply every ith row element, ith row jth column element with jth row and ith column element, and then we are doing summation of this, and because of that multiplication complexity, it is coming as a order of cubic complexity. Order of n cube will be the complexity that we will see in detail in next lecture. So now if we consider matrix, we are making that it is two-dimensional array, and as we are statically allocating a memory, we are making some maximum size two-dimensional array declaration. So here you consider that one matrix we have defined, which is of m 200 by 200. Like so, for 40,000 elements, it is going to store in this matrix, maximum 40,000 element, and whatever it's the data type it is, for every based on that data type, the memory will be allocated statically at compile time to store information in this particular matrix. Implementation of this, it is very easy. So this is the advantage of matrix, because at statically we are allocating memory, and just by making two nested loops, we can read the information, we can write data into matrix. So its implementation, it is very easy. But what are the disadvantages of this? If we consider disadvantage of this, it is a complexity. So if even though I have created matrix which is of 200 by 200, so for all the operations, its complexity, it is coming as a order of n square. Again, there is a wastage of memory. I have created a matrix which is of 200 by 200 size. Maximum it will store these many elements. But if I don't require that, then there will be wastage of memory. Out of this, only I may say 20 by 20, 20 rows and 20 columns are only present in that. Then I will say that remaining all the 180 elements, 180 by 180 elements, these are wastage of memory. Unnecessary, I have allocated memory to store that element. So that is a wastage of memory. Also, many times it happens that in the matrix, most of the elements, they are storing zero values. That zero will indicate that either it is a null value or it is not required that information we are storing. And still we have to consider, we have to allocate memory for that, as statically we are allocating a memory. So even we can consider the example of our recommendation. Suppose I have 100 users and I have 200 movies available. Now 100 users, they have given, I am going to store for every user is going to give rating for these 200 movies. But maybe the person hasn't seen all that 200 movies. Out of that, only he has seen 10 movies from that. So at 10 values only he will give some rating. Remaining all will be zeros. But as it is statically allocated memory for that, so that zero values also we are storing, and that shows that it is a wastage of memory. And this is major disadvantage of matrix. And because of this, to solve this wastage of memory problem, we are moving to the next representation method, which is a sparse matrix representation method. So what is actually sparse matrix is? Sparse matrix, it is a matrix, but it will store only non-zero elements in our matrix, originally whatever two-dimensional matrix we have. So it is going to store only values or the information at which non-zero values are stored. So sparse matrix, it is going to represent by a triplet where it will store row number, column number, and what is a non-zero term representing that particular element. So we can represent sparse matrix by using arrays as well as by using linked list as well as. So we have two methods of representation, array representation and the linked representation. First, we will concentrate on array representation. So how we are storing sparse matrix by using arrays? When we are representing sparse matrix by using arrays, we are saying that we are going to create a matrix that will be two-dimensional array where maximum three number of columns will be present and rows that will be whatever n number of non-zero terms are present in that matrix. So that's why we are saying only three number of columns are there. What these three columns are going to store? Row number, column number, and non-zero value. So when we are representing any matrix, converting any matrix into sparse matrix, at first row, or we may say that it is a zeroth row, there initially we will store order of that matrix, means in original matrix, how many number of rows and columns are there. So at zeroth row, number of rows, number of columns, and number of non-zero terms which are present in original matrix that will be stored. And starting from the first row, all the non-zero value entries we are going to perform. Constraint when we are creating sparse matrices, always information whatever we are storing in the sparse matrix, it is in the sorted form. First it is sorted on rows and then it is sorted on column. In the next slide we will see one example how we are converting matrix into sparse matrix. Consider that this is a matrix I have which is having 15 rows and 6 columns. But now here we can see out of this, so in this matrix I can store 90 elements. Out of this 90 element, only few, maybe 12 or 13 places are there where non-zero terms are present. So now these non-zero terms, only these non-zero terms we are going to store in your final sparse matrix. So how we are going to store? Assume that here again what is the advantage? If I am considering that I have created a matrix of integer, so 90 elements I want to store in this matrix. To store each integer element, suppose I am considering that I require 2 bytes. So I will say that 180 bytes will be allocated at compile time to store this particular array. But I know that only 13 rows are there, 13 elements are there which are non-zero elements. So out of this, I will say I'm going to store that information in my sparse matrix where it is going to store 13 non-zero values with their row number, column number, and non-zero term. And first row, it is going to store what is the order of my original matrix. So total 14 rows will be there and in every row 3 columns will be there. So memory required that will be only 84 bytes to store this particular matrix into sparse matrix form. So here we can say as 13 number of elements are there. So to store that 13 element, we are going to take 13 rows, and in every row number, column number, non-zero terms will be there. So in the next slide, we will see how it will be representing. So here you can see this is the sparse matrix where I'm going to create, this is a sparse matrix where at the 0th row, it is storing how many number of rows are there in my original matrix. So 15 rows are there. I'm going to store 15 value here. Then it will store number of columns. 6 columns are there. So at 0th row, first column, it will store number of columns. And at 0th row, second column, it will store number of non-zero terms which are present in this particular array. Now starting from the first row to 14th row, I'm going to store every entry in my matrix, which is a non-zero entry. So here we can say at the 0th row, second column, 1 is present. So it is at the first row, it is storing 0th row, second column, 1 is present. Then 0th row, fifth column, 1 is present. Similarly, at first row, 0th column, 2 is present. So like that, now it is one by one, it is storing the entry that I have in every row. At 0th row, at 0th column, I am storing row number. At first column, I am storing column number. And at second column, I am storing what is a non-zero value. So this way we are representing our sparse matrix. So here you can see one by one entry as 13 non-zero elements are there. 13 non-zero terms are present. So 13 rows to represent that 13 value, and 0th row, it is to store the information about original matrix, its order, as well as how many number of non-zero terms are there. So in the next lecture, we will see how we can perform addition of sparse matrix, how we can take transpose of sparse matrix. Till then, you can try out this example. This is a matrix given. Convert this matrix into sparse matrix. Thank you.